Okay, guys, good morning and welcome to integration. Right, like I'm saying, our topic today is integration. Please don't have the slightest mistake that we're moving away from differentiation. We're still in differentiation, we're doing integration. How do I understand this thing? The simplest way to understand the two things, integration, differentiation. Just take suppose that you have been moving to the east for the past 3 or 4 weeks, differentiating. If you are moving to the east, walking especially, you can trace your footstep backwards and find the way exactly back to where you came from. Then integration and differentiation is this kind of relationship. I start with a function here. I've intentionally used a different notation of a function here. Capital letter f of x. And this side, I'm doing differentiation. I learned at a function little f of s. So this is what I've been doing throughout these past weeks. So we want now to think of, is there a reverse process to go back to the same function there where we started? If I started with a 5 and added a 6, I'll land at 11. A simple question which is obvious is there a way I can do some kind of operation even if I don't know the name of that operation, but land back at 5? You understand what I'm saying? That's exactly the story we're dealing with here. Now, let's start this way. Let's suppose we've got these functions. There is the capital letter f of x. The paper I gave you has got this kind of a thing. This black line here, if I was moving along N1 going to Joburg, I would say this is a dual carriage. This is N1 south and this is N1 north. If I started from Tshwane and went to Joburg, if I use this other carriage, I'll land back at Tshwane. There's a demon here. Right, so I was saying if you had a highway like the N1, it is dual carriage. It carries traffic from Tshwane to Johannesburg, and from Johannesburg there's another carriage which takes you back to Tshwane. So you can say N1 south, differentiation, N1 north, integration. So that thing, listen, I don't know whether you've ever seen a place where you can go, there's no way backward. All together. So integration, if it's a process, it's important to see whether we can find a process which reverses that process. All together? Yeah. No, let's not go. Sorry. I think I just take that as a joke, because if we go to the issues of faith and the beliefs, my position is beliefs are not supposed to be rational. So we cannot talk about that one. So let's go. This thing is coming up, my friend. What's going on? Okay. Right now, so our task, guys, I gave you a kind of a paper with this kind of a situation. Let's start. 1. We know power rule, we know differentiation. Let's differentiate the first function there. If you look at this function and that function, the difference is that this one is plus 25 and that one is plus 0. All together. Can you please differentiate the function? Do it yourselves there and tell me what's the answer. You can discuss in pairs there and tell me what's the answer to that derivative. Right, you must write Please write the differentiation explicitly how you do it. So do the next one. In other words, I'm saying differentiate the next one. We started at x power n plus 0. Now do x power n plus 25. Try x power n plus minus 9. X power n plus 4 to the 5 to the power 4. Right. I think there must be something you're observing there. I want your observation. If you're doing correct, I think all of you must have a kind of one conclusion. Right. What are you getting? Who can tell me loudly what should I write? I'll write it in this box here. If you've got 10 answers, tell me you've got 10 answers. How many functions are there? 1, 2, 3, 4, 5, including C. And in those dots there are millions and millions of, say, infinite functions in between there, altogether. Plus a quarter, plus a half, or plus 10 to the power 7, and all those things. Is that right? So what I can say that we've covered there all the functions which start with x power n plus something. If you differentiate any of those functions like that, please tell me, answer explicitly showing how you do your differentiation. Tell me what's the final answer getting here. One person, please, who can tell me? Who wants to tell me the answer? But I ask the question first, are you getting 10 different answers or infinite different answers, or are you getting only one answer? One answer, that's good. First of all, then, next question, what is the answer you're getting? What's the result you're getting? Yes? This gentleman is saying he's getting n x to the power n minus 1. Good. All together? That's good. Let's come here. Let's look at these ones. Do exactly the same thing. Pick those functions one by one, differentiate them until you observe something. I'll give you about 2-3 minutes to if you observe, notice something, and it's something interesting, you must raise up your hand, please. Are you getting from there? One answer. Are you sure? Okay. What is the answer? Who can tell me the answer, the result of that differentiation you get from there? I'll write in the same square again. What is it? Can I have yes, Pinto? N of x, what does it mean? N multiplied by x to the power of n minus 1 plus k. Please, k there is any number. Altogether, any number is any number. Just like at the end there, you can add any number, and that number is symbolized there by c. But the k is a number, could be 5x, 6x, then you get something like this. So what is this telling? This is telling us that any function which belongs to this family with this kind of a structure, the first one there, we could just say this is plus 0. You differentiate it, you get only one answer. This will be the type of the answer. If you get something else different, and you are telling us that all of us here in class, we are wrong, then you must check something with yourself. Are we together? Okay, good. We move on. Let's differentiate this one, this type of function. I'll give you about a minute and a half to do that, and you give me your observation. You guys, you are experts in differentiation, I know. You must have observed and got me a response. Similar questions I would ask, which I have asked before. So I think you have asked yourself those questions, you've noted what you have noted. Mama Bull, can you tell me what's the answer?
N into x squared.
N?
Into x squared.
So N, so x squared plus 2 power what? Oh, you said N multiplied by. Okay, sorry. I'm sort of lost it there. Then you say N multiplied by
X squared.
x squared plus 50
To the power n minus 1.
to the power n minus 1 multiplied by 2x. Is that right? Plus 0 if you want to give a bonus, isn't it? Plus 0. Now, what can you observe there? What can you observe there? What you have observed, can you tell me what you have observed? Because we don't have 50 here, we don't have 50 here, we don't have 50 here. We've got different numbers there. But you must come up with a conclusion now. If you're differentiating a function like that, what changes, what does not change? Yes? What changes is the number, right? Yeah, but tell me all the changes we can see, guys. Tell me all the changes you can see. You can. I think I'm not saying I'm wrong, but I think you can be more explicit and more. I don't know whether the word is more explicative or what. I don't know. Some of these words are very heavy, but you can be more. Maybe make it more explicit. What exactly what changes you've observed? Yes. The constant number inside the bracket changes. No. I'm saying you differentiate this function, you differentiate that function, you differentiate that function, you differentiate that one. You must be able to just talk only about the changes. And then maybe you can comment, this will not change. What will change is this, the changes, the new things in this thing. What are the new things in this compared to what we have there? Yes, Krakud.
What I get from all the derivatives we do is that the derivative of a polynomial x function will always be equal to the derivative of that function plus the constant.
No. That's not the derivative. Just hold on. That's not the derivative. Okay, let me just help you to observe what are changes here. Given a function like this is a power function. The argument of that power function will not change. What are the changes? It will multiply by n, and the power will be reduced by 1. And the new thing is the derivative of the argument of the power. Do you see that? That's what I see is new. I'm comparing this, anything here. It has got a constant outside there. There is power plus 0. So when I differentiate, the constant disappears. That's the change. The constant disappeared because it's differentiated to 0. Then the next thing, the expression under the power does not change, but its power is reduced by 1. And having the power reduced by 1, there is a multiplication by the power n. The power which was there before was n, but that power comes now multiplying. Those are the changes I'm seeing happen. Do you see those changes? Is they important to notice? Are we together? Okay, so let's move on. Let's move to the next slide. Right. Carry on with that one. I'll give you also 1 minute. I think now you know how to differentiate. I'll give you just 1 minute to do that. Right? There I started with the x power 2. Sorry, sine x plus 2. I put the x in brackets there to emphasize that is the argument of the function. Is that right? Okay. So if you differentiate the whole of that lot, what did you get? Each one, differentiate one of them. This one is plus 0. This one there is plus 0. And the plus in between there got sine x plus any number, real number. What is the answer we're getting? Yes, my sister there. What are you saying? You are getting cos x. For this one, also getting cos x. Are you sure? Sin x plus c, you get cos x. Sin x plus 89, you still get cos x. Can you explain to me why? Then? Yes.
Derivative of sine is cos.
Hmm? Yeah, what she's saying is that we have got two functions here. Constant function 89 is sine function. The derivative of sum of the two is the sum of the derivative, isn't it? The derivative of sine is cos, the derivative of 89 is 0. And that will happen with any constant added to sine there. Then finally, derivative of all this family. Did you hear what I said? What did I say? I said the derivative of all this family with infinite members. I think your family has got finite numbers, people, isn't it? This one is a family with an infinity members. They all differentiate to cosine x. Isn't that beautiful? Huh? It is beautiful. And maybe you can say, if differentiation was a surname, we'll say the surname of these guys is cos x. They're in the same family, isn't it? Okay. I hope next time you don't find a different surname for a member of a family. Okay. Right. Let's come to this one. I like this. If you don't like this, then maybe there's nothing you'll ever like. This looks beautiful to me. How does it look to you? Are you sure? Beautiful. Right, guys, I think you must have observed something interesting now within this minute I've given you to try to differentiate this family, the members of this family. What can I write here? Like before I wrote one thing here, what can I write here? What do you suggest I should write? Chandra, what should I write? Who wants to talk? Yes? Let's don't swap around things for now. Let's just put them in order. Yeah? Minus, that is too small. Minus sine brackets what? X cubed multiplied by 3x squared. I've intentionally written that 3x squared there in red. You understand what I'm saying? Okay. How do I want you to read that? I want you to read that the derivative of each one of these members of this family is actually minus sine, retaining the same argument multiplied by 3x squared. And everybody can see that 3x squared is the derivative of the argument of the whole family. Are we together? Is that clear, guys? Good, man. Any questions up to that point? Are you still enjoying yourselves? So? Okay, if you're enjoying yourself, continue enjoying yourself. Now I've got this family. Let's try it. I'm happy to remind you that the derivative of tan x is sec tan. All together. The rest, I'm not. You see? Even a fox which is born on the tree and it jumps from a branch to branch every day from birth, one day it misses the branch and hit the ground with its buttocks. Like the lecturer also can make a mistake. So what is that? Let's be careful. I hope you notice that above there I've got tan. At the bottom there I've got a family of signs. So we're going to put one answer there and the other answer at the bottom there. But the observation must be the same. So you corrected, they said the derivative of tan is sec tan. You did? Oh, sec squared. What is the derivative of sec? I think it's Monday today. Maybe I've got some bubblers. Right, let's move. Now, let's get the first response there. Who wants to give us the first response there? Yes. Can I correct that into, please? It's n multiplied by, in brackets, then you read the thing. No, please, into n multiplied by, in brackets, n, in brackets, tan x, close bracket, n minus 1 multiplied by sec squared x. All together. Okay. Again, I want to emphasize that what I've written in red there is the derivative of the argument of the power function, and the power was power n. All together. And this is the derivative of the whole family. All together. Is that right? You differentiate any of this member of this family above this line here. Let's divide that bit there. All of them, they'll go to that kind of derivative. Next one. Who has got the response for that one? Yes, my brother? Is anyone else want to give me the answer? Yes? And n multiplied by?
Sin.
In brackets, In brackets?
Sin x squared.
Sine of x squared to the power n minus 1 multiplied by cos, let's see, cos x squared cos x squared multiplied by, I'll cheat there and write here, multiplied by 2x. plus 3. So here I'm starting to combine functions. You can see that I'm starting to combine different functions because I think we are ready for that. But plus 3 there, I think plus 3 I should have written it in different color. I should have written it in black. Let me write it in black because the red part I want it as a derivative of the argument of that power function altogether. So plus 3. I hope, can it be seen there? Can it be seen? Now my box there is too small. I didn't really recite this before. If I had seen that it was going to be like this, I was going to present something more beautiful than this. Altogether. But I hope you will take my apology there. That's right. Okay. Okay, it's fine. Let's go, move on. Yes. Okay, there's a mistake somewhere. Let's see, I didn't notice it. What is it? Derivative of who? Okay, the last equation just see. That was my mistake, sorry. That one was supposed to belong to the same family, sorry, that was my mistake. Okay. Okay. Thanks for that correction. My intention was to have the same families of the same family there. Functions of the same family. Right. Okay, thanks for the correction. Let's come to this family now. Again here, I presented two families. One family, natural base, and the other family, arbitrary base A. There's something missing there. Dot somewhere there. Right, get on with that one. This process is becoming easier and easier, and I think people can observe. They observed a lot of things here. Somebody just tried to give us an answer which we want in future, but let's get this sorted now. For the functions, this family of functions with the natural base E, let's get the answer here. Who wants to give me the answer? Yes, Mara. Yes? Yes, you. A to exponent x squared multiplied by 2x. Again, let's say a to the exponent x squared multiplied by 2x. Then the next one. Next one. Can they get a different guy to answer this one? Yes, Lamin. A to, sorry. A to power S power 5 multiplied by 5x to the power 4 multiplied by ln A. What I've written in red there are new things because the exponential function in differentiation bounced back exactly as it is. Then we highlight that it's accompanied by the derivative argument multiplied by the ln of the base. Now guys, I can go exactly to the first slide. Exactly to the first slide. I don't want to go there. I want to start from here. The question I can ask here, I want really to ask an obvious question which can be answered by everybody. At this stage, everybody must answer this question. If I were to ask you, this is a derivative. Actually, someone comes in here and said, little f is a derivative. Of what? Of which function? What did you say? Tell me. There are many answers you can tell me, but I want somebody who's going to pick the best choice of the answer to this problem. The question is, this is a derivative of which function or of which functions? But I want you to answer this way. You give me the best candidate of where this function comes from, which will maybe embrace all the functions, because you've been talking about the family, isn't it? Okay, who wants to answer the question? I see one hand here. Guys, I should see all hands, but you didn't see where this derivative come from. No. Who didn't see where this derivative come from? Those hands up, those guys didn't see the derivative where it come from. No. Listen, guys. Who tells me it doesn't know where I got this thing from? Who knows where I got this thing from? When I was writing this thing, you gave me this to write. Do you know where I got this from? Then the question is, this is a derivative. Where did we get it from? Can you answer that question? Who cannot answer the question? There's no hand up, meaning everybody can answer the question, is it? Yes? Tell me what to write. I'll write it here. Here. Where did it come from? From a to the power x squared. Only. Plus c. Can you? Plus c. Can you tell me about this c you're talking about? Tell me more about that c you're talking about. He says this derivative came from e to the power that plus c, and they're saying, telling me more about that. He said c is a constant, any number. Is it? Guys, I'm telling you, I think I'm going to kill somebody. If tomorrow I ask you, where did this derivative come from? You leave this c. Altogether. Did you hear my question? I said, here is the derivative. Where did it come from? This is how we write it mathematically. This is how we write it mathematically. The question is put this way. That's a question mark. I'm telling you that this is a question mark. It's a new question mark in mathematics. It does that. Then you write inside there, e to the power x squared 2x with respect to x. Meaning, here is a derivative. This question mark is saying, here, look here, it's pointing here. Here is a derivative. Where does it come from? Now the answer of already been given. We're not going to ask that again. The answer of already given. X, no, sorry. E to the power of x squared plus c. So what is integration? Integration is to reverse differentiation and that. If really we could call this differentiation an operator or a function, we'll say this function is evaluate all these functions, this one. If you pick n this function, its value will give us that. But this is not a function. We don't want to look at that differentiation. We can look at it as an operator or a process. It acts on the functions, gives us that for all these functions. Now, let's say this is D, the process D, differentiation for this D. Now, what is integration? Integration is the second process, the inverse process. Now, it will reverse what D did. Altogether. So now, if you tell me you don't know what is integration, then it's a problem for me. Integration is the reverse process of integration. And listen, this what I'm saying is that this is a question mark. I like it to say this way because I like it to say that way. I mean, somebody else says no. Why are you saying that's a question mark? I don't mind where that person is coming from. But to me, for the purpose of passing my message to you, my students, I'm saying this is a question mark. It says here is a derivative. Here is a derivative. Where did it come from? Question mark. Now, that is just illustrative. How do we write it normally every day in life? Every day in life. We just write integral e to the power of x squared x dx. Tell me the answer to this one. Tell me the answer to that one. Yes, my brother. E to the power is x. No. 1/2. No. First of all, listen to me carefully. Listen to me carefully. Whenever we differentiate an exponential function like natural base like this, it must come together with the derivative of its argument. Is there a derivative of argument here? No. What am I trying to say? There's nobody who's going to give you a problem of integration like I gave it to you there, like manna from heaven. No. We are going to give you this problem in such a way that you will be able to see whether you really understand what you are doing and you can do the relevant manipulations to get what you want. There is no derivative here, but check this. I write this e x squared x dx. And I see that there's no derivative here, but my derivative is short of something. What is it short of? It's short of a constant, especially a constant. Listen, I said short of a constant 2. Then I take that 2. I don't take a 2, I take a 1. I write 1 creatively. All together. Then I come and put it here. Then I say, I've got too many things under this integral sign. I don't need some of them. When I've got the derivative of 2 sign, I can just take 2 outside the derivative, just differential sign, isn't it? I can do that also when I'm integrating. Then I take this half outside. Then I do this. That 2 now, I write it in black. And then I do that. What do I have now? A complete derivative, isn't it? In other words, I did some kind of manipulation to compensate my derivative, which was shortfall of something. Now I want to write the answer to this one. It's exactly the same answer I've got there, isn't it? But that answer will be multiplied by this half. Sorry, there's an equal sign there. Then I write equals. That half will be there, multiplying the answer, which is, this is a derivative from exponential function argument that. How do I know that argument is that? I can see the derivative argument, the derivative. I can compare the derivative and argument. I can see, okay, this is the function. Then plus a c. Then I beautifully write this as e to the power x squared over 2 plus c. Guys, I think we're going to stop there. And then I can invite you now to go and open any book with this table of with this type of integrals and do as many as you can. And this is called indefinite integral. Thank you for listening. I think it was a great day.